We're going to continue to sort of lay the land for today, for the rest of the week, for everything we'll be talking about. And let's jump into it. So quickly, the fundamental truth about the Data Science Fellowship Program: statistics is an entire field. We are here for a week. All right? So it is impossible that we will actually cover everything in statistics over the course of just this 1 week. All right, other things that are true. Our field, astronomy, is driven by observation. So to narrow the scope for this session, to make statistics useful for a general group of astronomers, we're going to largely focus on data and models. Most of what we'll be talking about this week is data and models. So this leads me to one of my favorite questions to ask in the DSFP. What is data? Take a second to think about this. Cohort 5, smile to yourself. Okay. There's actually a lot of different philosophical approaches you could take to answering that particular question. But I'm going to make a generalization, perhaps an overgeneralization, by saying that in astronomy, data typically come from measurements. And now I'm going to introduce an idea that you maybe have not heard before. And that idea is that measurements are constant. What does that mean? Once a measurement has been made, the measurement has been made. It does not change. Measurements do not change. Furthermore, all measurements, this is a fundamental limitation of physics, of how we understand how the world works. All measurements come with uncertainties. So if you're going to perform analysis, you're going to build models, you should account for these uncertainties. All right, so let me ask another question. What is a model? Typically, models are constructed to explain data. And we generally use models for one of two purposes: forecasting and inference. Forecasting is about predicting some future outcome, right? Predicting some as of yet unobserved event. Now, even for us astronomers, this can be incredibly cool, right? Suppose you have measured the velocity dispersion of the central region of some galaxy. This actually then will allow you to hit the mass of the black hole at the center of that galaxy. We can come up with many other examples throughout our field. Inference is about understanding the fundamental relationship between different parameters. Inference can be used for forecasting. So if we do a bunch of experiments and then we conclude that in some electrical circuitry, V is equal to IR, right? We can then predict, if we have some resistance and we have some voltage, what's the resulting capacitance that's going to be in some circuit. But that's also a fundamental relationship about physically what's happening in the circuit, the equal dial. But we can't always use forecasting models to truly understand the underlying physical relationship for whatever it is that's being forecasted. Right. So as another example, right? It can be incredibly useful to say, I have made 10 measurements, and when I apply a force to some ball, I predict that some newly applied force will produce an acceleration that is equal to whatever this new force is divided by the mass of the ball, right? But again, that's useful, but it's not the same power as being able to say force is equal to mass times acceleration. And it's that latter, right? Those are the insights that truly change the way that we understand the universe. We make some physical inference that says, oh, this is why something looks the way it does. Right? And we can use those principles to understand other things as well. Okay. So, as I said before, the focus for this lecture and for most of the rest of this session is going to be on a building model. Right? Okay, so that brings me to problem 1. Consider the following data. What can you infer about these data? Please take a moment to discuss this with the person sitting at the table next to you. What can you infer about these data?
No, that makes sense. I would say the line here and say that these points are outliers. What do you think? Yeah. It can have some linear relationships.
I'm not entirely sure.
I mean, what can you say about the data that's labeled for the graph? Yes?
I mean, I get the sort of thing, but
I mean, it was also probably like easier to measure like for lower axis than for like higher axis because we have a lot of points there.
All right, let's try to wrap up in the next 30 seconds.
Yeah, we have non-constant uncertainty. Right.
Wow, you actually wrapped up in 30 seconds on your own. That is literally the first time that has ever happened in the DSFP. All right. Anyone like to share what they discussed?
As an astronomer, I would still align to that, but inferring about the data itself, I'd be likely to infer that they are correlated, and my mind would want explanations for the outliers instead of saying the outliers disprove the correlation.
All right, so we've used a lot of terms here. We've added a lot of terms to our discourse. We heard the phrase outlier. All right, we also said we could maybe fit a line because it looks like perhaps there is a linear relationship between these data. Okay, anything else? Yeah, Tony?
we have here discussed that you could classify this blank space between 100 and 200 at dash. You could classify any on the left side or any on the right. It's like disturbing to see that clumping too, right?
Okay, so there it's possible that there's maybe some underlying classification that can be applied to these data. Yes? Okay, Suzanne?
X doesn't have any error bars, so it might be an closer to a measurement.
Okay, so from the visualization as shown, there is no uncertainty on the X values. Yes? Yeah? Okay. Yeah. Cool.
So Y errors seem to be symmetrical as well.
The uncertainties in Y are symmetric. Yeah? Yeah.
We're not really given much information about what this is measuring. So outside of describing what it generally looks like, we give the full physical information.
Mm-hmm. There's very little information here, and there's nothing that we can physically understand about this particular system. Yes, all of those things are correct, right? So all great observations from all of you. But very technically, that's just a bunch of dots on a screen. Yeah, so there's not a whole lot that we can actually infer without getting more context, right? What is X in this case? You know, it's funny, every plot we make has X, and yet I have never once in my life measured an X. Have you? What is Y, right? How was this data collected, right? We heard some terms like outliers and terms like linear relationship. But can we actually be sure that any of those things may or may not be present in what we're looking at if we don't know how those observations ended up in that visualization in the first place? Okay, so here's the answer. Those are all made up numbers that I generated with a random number generator. Okay, moving on. We're going to assume that there is a linear relationship between the data that was just shown on the X and Y axes, right? So this means we can construct a model to explain these data. So this brings me to breakout question number 2. What is the best fit model explaining the relationship between X and Y? Why don't you take a moment to discuss that with your partner? Yes.
I don't know it.
I mean, I would say the line. Like if you take polynomial, for example, you might overset.
I think I'd actually try to fit them all.
Like what's the order? Yeah, that's like
3 or 4 order.
Yeah, that's the danger. If you fit like large order polynomials, you might overfit.
I'm not entirely convinced that that's linear.
I mean, sure, it's not necessarily linear. Like it's not a line, sure, but like linear model might be like one of the ideas, one of the ways.
All right, let's wrap up in 30 seconds. That was 9 seconds. You all are way too well behaved. All right. So the question was, what is the best fit model explaining the relationship between X and Y? Would anyone like to share? Jake?
You got a really good fit by really overfitting and using like a 30-degree polynomial to every point.
Okay, so you could do something like fit a 30-degree polynomial and then have some model that more or less goes through all of the observations.
We were saying that typically you would want to fit the simplest model that you could, because sometimes you'll get overfit, and if you don't actually understand what's happening, physically, obviously there's nothing happening physically. It's not really beneficial.
Okay.
Yeah.
So we're adding more terms to our discourse now. So we had a discussion of overfitting, right, which means a model that basically is a lot of ways to explain this, over-conditioned on the data. So typically an overfit model will do a poor job of forecasting. Yes, so simple models can help prevent overfitting. Other ideas?
I feel like it really depends on your objective, because if you're looking to fit something with a functional form, then maybe like linear polynomial fit would be really helpful. But if you're just looking for a pretty line with the data, like use something like maybe like a lowest regression that would adapt to the data itself without like a distinct functional form associated with it.
Okay, yeah, so I'll paraphrase slightly and say you can develop some like non-parametric or data-driven methods that don't specifically assume a direct functional relationship between X and Y as an explanation for what's going on. Yeah. All right. So when I was first taught statistics, which was a long time ago, The method I was taught at the time literally was guess and check. So basically, guess a solution, draw some solution, and then somehow measure the quality of that solution. Or in the very simple case, just look at it and say, pretty good. All right. So I did that. That's how I started today to figure out the best fit model for these data. This is what I came up with. I only saw one person go, Most of you don't like this, maybe. Okay.
I like it.
Several of you like it. All right. Whatever. This is a guess. What's the problem with just a guess? There's almost no way that we can say with any sort of certainty that this guess is best fit. Right? Instead, we should probably develop some form of numerical measure of what is the best fit to these particular data. Okay, so let's come up with some other ideas. Well, one possibility is we could just look at the residuals, right? We're going to build some model. In this case, we said it's linear, so we're going to draw a line. And we want the line that minimizes the sum of the residuals. This is called the L1 norm, and it looks like this. Okay, the dark line now on the screen. It looks fairly different from the best guess. If you like it better, maybe you don't. At least it's numerically driven, this particular solution, right? Maybe you're like, I don't like residuals. I like residuals squared. Right? So then you want to minimize the sum of the residuals squared. This is the L2 norm, or this is what's very often referred to as least squares fitting. Okay? Many times this is sort of the introductory method for how you fit a model to data in some introductory statistics course or data analysis course, right? That line looks like this, the dashed line. You'll notice the slope is very similar to the L1 norm, okay? But it's almost like the entire line has been shifted down. And that's due to the presence of the data points that lie very far from the line, right? So if we're squaring the residual, the terms with the largest residual are going to be more influential on a point-by-point basis than the other points. Okay? So that's why the line moves down in that case. That's why least squares gives you a different best fit than the L1 norm. All right, well, what if you're like, screw all this first order, second order, I want the residuals to the 100th power. What do you get then? Okay, you get this thick line, whatever, I don't know. There's no reason to do this. Please don't. Okay, all right, so, wait. Beginning of the talk, I said, don't forget the uncertainties, and we haven't considered those at all. That's not good. All right, maybe best fit is if we minimize the square of the residual divided by the uncertainties. Because then, if you have some observation with some incredibly large uncertainty, even if it is quite far from best fit, it will not have a lot of influence on your final result. Sometimes this is referred to as the chi-squared. We'll come back to that. So in doing so, we can actually downweight, right? We can say things with very large uncertainties have less influence on the final outcome. What does that look like? We're now hitting the point where there are too many lines to know what's going on, right? But the short dashed line is the minimum of the chi-squared, or the residuals divided by the uncertainty. Or is the best fit just the actual relationship between X and Y, the thick, solid cyan line that's just been added? That line is the actual relationship between X and Y. I know because I created the data. So is that the best fit? I see people saying no, but that's the answer. Okay. All right. So which one is best? Which of these is best? So for that last one, right? I simulated data. I can tell you what the answer is. But will you ever do an investigation of nature where you know the true relationship between the variables you're looking at? The answer is no. All right. Okay, so I want to talk about formalizing this idea of best fit a little bit more using something called the likelihood. So building on this morning's lecture, we can use probability theory to actually derive some numerical sense of what is best, which model is best. So if our measurements follow some known behavior, then we can write down the probability of every individual observation as a function of some model that we would like to test, which we'll call M. And that model will depend upon model parameters, which we will call theta. I suspect, although I don't know for sure, that similar notation is going to be used throughout the rest of this. So theta means model parameters. In the case of fitting a line, that is the slope and the intercept. But if you want to build an arbitrarily complicated model with tons of parameters in it, theta is still the parameters of that model. All right. So in the special case, and the often assumed case, where you have uncertainties that are Gaussian, right, then the probability of any individual observation is just defined by the normal distribution, written here in its full glory. So X is your observation, mu is the mean of your model, okay, and the variance is described by sigma squared. So this is just the probability of some observation given some model described by normal distribution. Right? So if we have many different observations, each of which is independent, meaning there's no correlation between successive observations, then we can define the likelihood of all of the observations as the product between the individual probabilities. So every one of those x's that we had in our previous plot, right, we just have a probability for what the value of that observation is given some model parameters. We multiply all those probabilities together, and that is the likelihood. All right. A quick note, the likelihood is not itself a probability distribution function. This is not something that you can integrate and then it's equal to 1, right? Every observation is described by its own probability distribution function, and then it takes on single value once that observation is realized. And we multiply all of those together in order to get the likelihood. So the likelihood is not normalized, and it's typically a very small number. We'll see this during the exercises. Okay. So again, for the special case, where all of our uncertainties are described by Gaussian, the likelihood is then equal to the product of this is just the normal distribution equation here. Okay, so we're just multiplying all of those probabilities together. With observations x sub I, so I make many different observations, and uncertainties sigma sub I. All right. Because the likelihood is typically a very small number, we often work with the log likelihood instead of the likelihood itself. All that means is we take the log of the likelihood, that turns into the following equation. What's nice is that these first two terms, we have a term that is dependent upon n, the number of observations we have, second term that is dependent upon the uncertainties on those observations, but those uncertainties are unchanging. So these first two terms are constant. So the log of the likelihood is proportional to the sum of the difference between the observations in the model normalized by the uncertainties, all of that squared. So what is the best model? I am here to contend today that the best model is the one that maximizes the likelihood. Or said in another way, the best model gives you the largest collective probability over all of your observations or given model parameters. And recall, right, our measurements are unchanging. The likelihood is a function of both the observation and the model parameters, but because our measurements are fixed and unchanging, then the likelihood is just a function of our model parameters theta. And so if we want to maximize the likelihood, we want to find the highest probability solution, we can do that by varying the model parameters to find the choice that best matches the observation. So our data do not change, our model parameters change. This is a subtle idea, and if you're kind of like, no, I don't believe you, Adam, it's okay. We'll discuss it during the problem. All right. Okay. We had a brief preamble about frequentist interpretations, frequentist statistics, and Bayesian interpretations and Bayesian statistics. We could do a whole week sort of talking about different points along these lines. Instead, what I'm going to do is sort of define the tenets of frequentist statistics, and then we'll spend the rest of the week talking about Bayes. Okay. There are three, so as we said, there are frequentist and Bayesian approaches, all right? And one thing that I think is important, and I think doesn't always get treated appropriately by astronomers who have very high horses upon which they sit, is that neither frequentist statistics nor Bayesian statistics is wrong. Okay? They are both approaches for understanding some observations that you have collected. Okay? And the other thing I want to say is that, as is true with everything that you will approach in data science, you cannot just say, I do blank, where blank could be machine learning, or blank could be frequentist statistics, or blank could be Bayesian inference. You cannot pick one of those things and adequately solve all problems. So while there will be a strong focus on Bayesian inference throughout the rest of this week, it doesn't mean that you always have to approach every problem in that particular manner. All right. So there's three central tenets to frequentist interpretations. Right? The first one is that probabilities are relative frequencies of events. So what this means, to go back to the example we had earlier today, if you are flipping a coin, all right, the probability that you will get heads or tails is essentially what you find in the limit of flipping a coin many, 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 many times and charting down what the results are. In the frequentist interpretation, parameters are fixed, unknown constants. Okay. So this means that, to go back to an example I had earlier, if you're looking at the velocity dispersion of the center of a galaxy and the mass of the black hole in the center of that galaxy, there is actually a single number that is true and correct for explaining the relationship between those two variables. So constant is what describes that. And then finally, the tenet that statistical procedures should have well-defined long-run frequency properties. This again means in the limits where you can run a test, an experiment with some probability many, many times. You flip a quarter, literally 10 million times. If you flip it 10 times and then you define a confidence interval, so you say, after flipping a coin 10 times, I have a confidence interval that brackets the correct answer to be between 0.4 and 0.6 in terms of how often I land on heads. And you say that you are 95% confident in that answer. It means that the 95% of experiments that you would run, you would actually get an answer within those brackets. Okay. I'm done with the frequentist now. I mean, we're going to look at models and building models in the frequentist paradigm, but that's all I'm going to say about that today. Okay? We'll hear more about how interpretations differ if you're working in a Bayesian paradigm later today and tomorrow. All right, so we've talked about likelihood and how we can look at collective probabilities over all of our observations to try and understand what is a best model. Now I want to talk about, okay, how do we actually maximize the likelihood? All right. So in order to do this, we actually have to start with coming up with some model that describes how the data were generated. And this can be as simple as just what is the relationship between y and x. And the model parameters that provide the largest value of the likelihood, that is the best estimate for those parameters. That is the maximum likelihood estimate. Yes.
Can I ask a question?
Question.
Yeah, so when you computed the maximum, not maximum, when you computed the likelihood function, I think you assumed that the data points are uncorrelated, they're like independent of each other.
Yes.
That's not the case usually.
Okay, yeah, so the question is, earlier, the formulation I gave for the likelihood stated that we are assuming that the observations themselves are uncorrelated, and then what if that is not? What if that's not the case? So we can recast the likelihood in the way that it was written here in order to account for correlations between observations, so should they exist. As I'm saying this out loud, I don't know that that's going to come up very specifically at this particular session, but a common way to deal with that is by using something called the Gaussian process, and we will cover that in a future session. Okay?
That's what I want to hear.
Okay. You knew the answer, you just wanted me to say it for everybody.
No, yeah.
Okay. Yeah, all right. So, yes, okay. So we are assuming for basically this lecture in the notebook that our observations are not correlated, but you can still write a likelihood in the situation where your observations are correlated. Okay?
Yeah,
so you can deal with both the situations.
Yeah, I'm sorry. I asked that question because that's like the formula that you gave for likelihood. It's like, is the formula that they see all the time.
Yeah.
But I'm like, but you stated there that's for like independent parameters.
Yes, that's right.
Yeah, and so now I'm like a little confused. Like what usually parameters are not independent.
Well, so yes, the assumptions and the equations I showed are that the individual observations are independent.
Yeah.
So the probability for each observation itself is independent, which is why you can multiply them all together in order to get the likelihood. But you can write a very similar looking but different equation that accounts for if there are correlations between the individual observations. So you can still write a likelihood and you can still maximize it, even if the assumption that we started with today is not valid. Okay. All right. All right. In some very, very simple cases, all right, it is possible to actually take your equation for the likelihood and differentiate it in order to get the maximum. Just do a little bit of calculus and you actually get the maximum, right? But typically, as soon as your model gets even, a little bit more than fitting a polynomial to the data, this is no longer the case. And so we use numerical methods typically to find the maximum of the likelihood. Maximizing the likelihood is equivalent to minimizing the negative log likelihood. And I used to know the answer to this, and I've now forgotten it. But for whatever reason, numerical methods always try to minimize functions instead of maximize them. Does anyone in the back of the room remember why? I don't remember why. I used to know. We'll look it up during the break.
I mean, I think that machines work better with small numbers.
Mm-hmm.
So maybe that's why they prefer to go down. Work better with small numbers.
Yeah, that sounds reasonable. Yeah, so it may be that it's just easier to descend as opposed to going up when you could run away to potentially infinity quite easily. Okay, so you'll all get a chance to do this, but the standard function in Python, if you want to minimize a function, is called minimize. Python folks, they know what they're doing when they name stuff. And that is inside of SciPy Optimize. All right, I'm not going to go through the details of that in very explicitly right now, but you'll see that in the notebook once we start working on the problem. Okay. But there's an important caveat that we should all be aware of when we're using numerical methods to try to find a maximum or a minimum in the case of looking at the negative of the log likelihood. And that is that there is no guarantee that whatever method you are using is going to converge to a global minimum. So typically the way these tools work is you have some multidimensional space. You're essentially moving in that multidimensional space to locations that have successively smaller and smaller likelihood values, right? Until you get to a point where any direction you move, the likelihood value would become larger. And so then the machine declares you have found a minimum. For complex problems, it is not hard to find local minima. This is just one thing to be aware of. You'll see this in the notebook itself. This is also not unique to a frequentist interpretation for doing maximum likelihood estimates, right? If you were doing some Bayesian inference and trying to find optimal model parameters, the only way you can guarantee that you find the optimum is for running your computer algorithm for an infinitely long period of time. Raise your hand if you would like to be done with your PhD infinity years from now. Just one of you. We'll talk during the break. Okay, so again, one thing that's very nice about assuming a Gaussian likelihood is that you can recast the likelihood in terms of the z-score, where z is just your model, is your observation, the difference between your observation and the model value divided by the uncertainty. Okay? And so then your log likelihood is just equal to -1/2 the sum of these z-scores for each of your individual observations. This sum, the sum that I'm showing here, this is what the chi-squared is. What's nice about treating things as a chi-squared is that chi-squared is an actual distribution. And I put a little bit of extra bonus slides in my talk that I'm not going to show now, but you can look at those if you want. What's nice about casting things in this way is that your observation, right? You cast everything in terms of, chi-squared is a distribution. Right? So if you write in your likelihood in this way, the results of your likelihood, the probability of your likelihood can be cast in terms of the chi-squared distribution. We'll talk more about common distributions tomorrow. Okay. All right. That chi-squared distribution itself only depends upon the number of degrees of freedom in your model fit. So this is just the number of observations you have minus the number of model parameters that you have adopted. Okay. So this is quite nice. Sorry, one other thing before I say that. So as we heard earlier, right, if we have a whole bunch of observations, we can just create a model that has a whole bunch of parameters, and eventually we will have a model that more or less goes through all of our observations. So it's possible to improve the likelihood. One way to improve the likelihood is by just adding additional parameters to your model. If you have 20 observations and a 19th degree polynomial, that 19th degree polynomial will literally go through all of your observations. Your residuals will be 0. And so for this reason, it's often convenient to define the chi-squared per degree of freedom, which is just your chi-squared value divided by the degrees of freedom. Typically, this number, that particular chi-squared distribution, it has a mean that is equal to 1, right? So your chi-squared per degrees of freedom has a mean that's equal to 1. What this means is that very quickly, hand weightedly, if you calculate the chi-squared and divide by the number of degrees of freedom, you should find that you have some value approximately equal to 1. If you have some value that's much, much greater than that, then that means you likely have underfit your data, or the uncertainties have not been estimated correctly. They have been underestimated, to be specific. And if you have models with a chi-squared per degree of freedom that's much, much less than 1, it's likely that you have overfit your model, or you have overestimated the uncertainty. And so we now actually have a numerical measure to go back to our question about goodness of fit, right? Or best fit. Right? Generally speaking, models with a chi-squared per degree of freedom are good. Chi-squared per degree of freedom approximately equal to 1 are good, while those that are not are bad. Now, look at the distribution in the slide. The number of degrees of freedom matters in terms of what it means to be close to 1. Another caveat, using one of the terms that was introduced earlier, outliers totally junk up any sort of interpretation you might do by only looking at something like the chi-squared per degree of freedom. Okay. Nevertheless, we actually now have a numerical way to compare models. So we can pick model parameters. Here's a slope and an intercept. Ones that I guess are ones that I find by numerically maximizing the likelihood. And we can look at the chi-squared per degree of freedom to figure out which model is best. Generally speaking, I will say that chi-squared per degree of freedom, even though it's all over the literature, although it is becoming less popular with time, has too small a penalty for adding additional terms to your model, adding additional model parameters. Okay? So another way to compare models is with the AIC, the Akakai Information Criterion. Okay? This is very common in frequent statistics, right? So the AIC is just the negative of twice the log likelihood plus some terms that are related to how many model parameters you have, that's K, and the number of observations that you have, N. Models with the smallest AIC are preferred. Right? So what is this saying? If we have two models, right? You have a model, I have a model. Each of those models produces the same likelihood. So the probability of understanding all of the observations collectively is the same for these two models. Your model has 3 parameters. My model has 25. The AIC is saying that, okay, well, based on the likelihoods, these are the same. But now we're going to add a large penalty term, 2 times 25, 2 times 25, times 26, right? Because my model has many, many parameters. And so I'll have a larger value for the AIC than you do. Question?
This might make more sense after the end of this slide, but when can you claim new physics? Like when can you say, by adding this other term to a model, this like totally improves the chi-squared per degree of freedom, this totally improves the AIC, so therefore I can claim that my data is telling me there's some new thing here that we haven't counted for.
Okay, so the question is, at what point do I win a Nobel Prize? Because I have found some new form of physics, or how do I definitively state this model is superior to some other model? So the answer to that question depends upon the paradigm in which you are analyzing your data. So the answer is a little bit different if you're doing things in a Bayesian fashion than a frequentist fashion. But from a, strictly speaking, from a frequentist standpoint, you would use the AIC and you would say, here's a model. This is, let's say, commonly accepted model. And I fit that to the data and I arrive at an AIC value of whatever. But I have some alternative model and my model produces a smaller value of the AIC. Then you would declare that your model is superior and you have something that is better than whatever was in the previous model. Okay?
Does it like depend on the, like just that it's better? Is all it depends? Like it's not, 50 parameters versus 51. I'm just like stating numbers.
Yeah, so if you, in short, using this criterion for evaluating models, the model that has the lowest value of the AIC is the best model. Okay? So if you add one parameter to your model and the AIC goes down, then you would conclude under all of the assumptions that we have gone over earlier today, that model is the best. Okay. Yeah.
Where did these AIC designations come from? Like, what's the intuition behind the 2 last terms? Or from the side that, I have fewer parameters, it's going to be smaller terms.
Yeah. So I normally love knowing the history of why things are the way they are, and I am not going to get it perfectly correct. There is, so the short answer is that people were not particularly satisfied with just doing something like the chi-squared per degree of freedom. They wanted to introduce a larger penalty for adding more model parameters. And I forget the precise intuition for why this was written down. There are other information criteria out there, which I didn't want to go into all of its messy detail, that have different penalty terms in terms of adding more parameters to the model. So there are different ways that you can define what's going to be best. I don't have I will look it up and I will help you develop intuition for exactly where those terms come from, but I don't remember the history right off the top of my head. Okay. Yeah, Sean.
something I don't understand. I'm kind of, I should have asked it earlier, but so you started by assuming that the observations are drawn from a Gaussian, right?
We are assuming that the observations, the probability of the realized observation based on the actual underlying physics that drives the realization of the observation itself has a scatter, which is described by a normal distribution.
Okay, and then you define a likelihood for that. So if you just go to the thing for each observation, you have a different mean and a different standard deviation.
Yes.
Okay, and then you multiply them, define the likelihood. So when you maximize that and you have Gaussian probability, what do you get and how do you predict for new values? I'm not sure I understand that.
So in the equations that we've been looking at, we have had a lot of x's, which means the observation itself. This is confusing because on the plot we showed that's actually y, is what that refers to. And then we have a mu, which is the mean. If you have a line, mu is just the value of the line at the same independence variable where the observation occurred. So if we have some observation at y equals 50, x equals 25, right? Mu is just what is the value of the line at 25. And so we're comparing, right? We're saying that we have the observations are follow a normal distribution relative to this mean relation. So we're just saying, okay, if this is the line, what is the probability that I get any particular observation? What is the probability that I get all of these observations? And we want that, right? We want that product, we want those probabilities, all of them combined, to be as large a number as possible. That's what it means to have a maximum likelihood.
And how do you predict for a new x, for a new x-axis? How do you predict what's the y for that?
Well, once we have a maximum likelihood estimate, we have model parameters. So we now have an equation for a line. So pick any value x, and I can tell you what the value of y will be. Okay. All right. Okay. All right. So now just a few closing thoughts. So I wanted to connect today data and model, right? And I want to also say that whatever statistical philosophy you prefer, right? I strongly encourage you to think about likelihood as you make your connection between your data and your model. And we spoke only briefly today. We're going to talk about this more over the course of the week, but briefly we discussed model comparison, right? And how you might select the preferred model given some data set. But I want to ask you one last question in parting. And this question may bother you. What is the probability that some selected model n, what is the probability of some selected model m? So for our example we've been using today, a line, right? What is the probability of that model given the infinite set of possible models m sub I? For any data set, you could write down an infinite set of models. Right? So what is the probability that the model you've written down is correct? This is an intractable problem. In fact, I would contend it's an unknowable problem with no answer. Okay. A single model can be identified, all right? You can show that it is superior to others, but there isn't actually a mathematical, statistical proof to say that your model is right. Okay. All right. I hope that you all sleep okay tonight after hearing this. I basically didn't work for a day after I figured this out the first time. All right, so that's all I have today on maximum likelihood estimate. If you open up the notebook, we'll now get started working on some problems. Sorry, before the notebooks, I forgot to say, what questions do you have? Brian?
How about the effect that outliers have on type of innovation? How do you determine if you have outliers?
How do you determine if you have outliers in your today's set? So I mean, in some respects, right? So the question was, how do you determine if there are outliers within a data set? I just go with gut. Normally, I just follow my gut. No, that's not what I do. Defining something as an outlier requires, of course, some assumption about a model that you otherwise are declaring to be correct, which we just said is actually not ever possible. But if for some reason you are guided either by theory or by previous experiments that have been conducted to believe that there is a very specific relationship that should describe your data, then you might be able to identify observations that seem inconsistent with some relationship. What I would say, what I think a lot of people, I'm repeating other people that are smarter than me, is that if you're building models and you find outliers, probably the thing that makes the most sense is to build a little more complexity into your model. Because if you look at something and say, this is an outlier, well, it's an observation that happens. So something is generating those particular observations. And you can try to model that process, even if it's not perfectly well understood. That's a long answer that maybe doesn't totally make sense right now, but I really think it'll make sense before the week is over. Yes, Al.
So let's say I have the same data set that the
Okay.
and say I consider some models that I think could fit the data set. I mean, I'm talking from the point of view that your model can be right. So say I consider those models and somebody else comes up with some model. I've already made my model predicted, okay, this prediction, and then say maybe analyze, and then I conclude, and then somebody else comes with a seemingly better model. How do you go about to report it without making the other model inconsistent with it? Not right. I mean, to invalidate.
So I'm gonna repeat the question, and if I'm not quite repeating it correctly, let me know, but so people can hear. So suppose I have some data set, I've developed a model, I believe the model to be correct, so I publish it, and then someone else looks at the data set and they have some alternative model that they fit the data, and they say, I believe this model to be superior, and then they publish that. That, I would say, is essentially science, right? So the creation of a model as an explanation for data is effectively a hypothesis. And so different groups, different researchers coming up with or developing alternative models for explaining phenomena is something that has been happening throughout the history of science. And what's quite nice is that once hypotheses are developed, we can test them by collecting additional observations. So in the scenario you described, I have some model that I really like, someone else has an alternative model. Then the way that you figure out which one of them is superior is by going out and, your models are entirely based on photometry. Go take some spectra and see which one matches the spectra better, or something along those lines. So we are constantly revising our knowledge. Right? We are constantly building models, building explanations of the universe that are superior to whatever we thought 10 years ago, 20 years ago, 100 years ago. And that's because people are coming up with new ideas, and then we test those ideas with experiments. Okay. All right. It seems there's no further questions, so let's start on the notebook. Remember, you're here to work with the person sitting at the table next to you, and we'll be walking around answering questions as they come up.